Okay, so good morning, girls. Today I just wanted to go over how this question that we've been dealing with since the last 3 or 4 classes now. The question is it possible for two normal parents to have a child with sickle cell anemia? And hopefully after video 5, you saw that it is indeed possible. So I want to show you how this question and what we did with the sperm and the egg combining in fertilization in the last video, how that relates to the Punnett squares that you're so familiar with from middle school, or maybe you never had that in middle school. So you may have seen these before, you may have not. So I just want to go over what Punnett squares are really quickly. So the Punnett square is a model, and you've been hearing lots about modeling and the COVID model, and we modeled mitosis with chalk and when we were outside that day. So a Punnett square is really just a model, and it was named after Reginald Punnett and Reginald Crundle Punnett, who lived from 1875 to 1967. He was a British geneticist who co-founded with William Batesian in the Journal of Genetics. He published this model in 1910. So Punnett is probably best remembered today as the creator of the Punnett square, a tool that is still used by biologists to predict the probability of possible genotypes of offspring. So what we want to focus on there is that it's a tool and it's used to predict the probability of possible genotypes of offspring, meaning that if you have two parents and you know they're given alleles, what is the likelihood or the probability of the genotypes of their potential children or their potential offspring? So we're going to use a Punnett square today to show how the Punnett square is related to the question that we've been asking so far. So we're going to go to page 24 of your handout, and let me just grab my Sharpie here. I love a new Sharpie. I don't know if I don't have any brand new Sharpies. You know I love a good Sharpie. This is a pretty good one. Okay, so remember from the early in the unit, we said that A is represents capital A, big A, stands for normal hemoglobin. It stands for the normal hemoglobin allele. So if you have the big A allele on a chromosome, right, it stands for the normal version of hemoglobin, which looks like this. So if you have a big A, that means that it codes for the protein hemoglobin and it's normal. Okay, now little a codes for abnormal hemoglobin, which we also have been calling sickle cell hemoglobin. Okay, and we know, so abnormal hemoglobin looks like this if we model out the protein. Okay, so because normal hemoglobin, when you have two different alleles, say you have a big A and a little a allele, if you have a big A and a little a, it seems that you only have the big allele if you have two different alleles on your chromosome 11. Therefore, because we only see normal hemoglobin in a person, well, when you look at the person, they don't have sickle cell disease, we say that capital A, normal hemoglobin, is a dominant allele. It's a dominant protein, okay? Whereas if you have little a and little a, I'll show you that right there, you have sickle cell anemia or sickle cell disease. So normal hemoglobin is dominant because when an organism has two different alleles, it seems like the big A is the only one affecting the trait. Okay, so let's cross or let's mate our parents here, and we're gonna write down their genotype. So a cross means a mating. And we remember that cross, that kind of multiplication, that X from the first day. We're going to mate a person that has the genotype big A and little a, and the other parent is going to have the genotype big A and little a. So this will be mom's genotype, and this will be dad's genotype. So what that means for mom, I'm going to do mom in red. Okay, mom has a big A and a little a allele on her 2 chromosomes, and dad has a big A and a little a on his 2 chromosome 11s. Okay, so let's go over what happens. Well, here's our mom. She's big A, little a, and because of meiosis, right, only one of these 2 chromosomes, and these are homologous, only one of these 2 is going to end up in the egg because mom only passes on one of these possible 2. So in one egg, she can give big A, and in her other type of egg would have little a. So what I want you to do is draw that chromosome in that egg there, and let's put the little line on it. Mom's egg could have a big A allele, or it could have a little a allele. Hey, Mr. Eggy. I could have a big A, or I could have a little a. You don't know. Okay, now let's go over to dad's sperm down here. Dad also has the genotype big A and little a. So what that means is that his sperm could have a big A chromosome or a little a chromosome. Because of meiosis, only one of these 2 chromosomes is going to end up in the sperm. So is the sperm going to have a little a, or is the sperm going to have a big A? Again, dad's going to make both kinds of sperm, but you don't know which one will be used in fertilization. So dad makes sperm that has either a big A or a little a allele. You don't know. He makes 2 kinds of sperm. So what happens is that these 2 chromosomes, these 2 cells that carry these chromosomes are going to come together in fertilization. So what we're going to do is draw the 2 chromosomes with their alleles. Okay, we've got a big A over here because dad gave the big A and mom gave the big A. So what we see in this box is a zygote. It's a zygote. Pause the game. So this baby here, this fetus, could be the result of a big A sperm combining with an egg that had the big A chromosome. So what you have in this box is this little fetus here, right? She's got 2, he or she, we don't know, has 2 chromosome 11s. And if a big A sperm fertilizes a big A egg, you're going to get a zygote that has the genotype big A, big A. And so we're just going to continue that down over here. Okay, what happens if a big A sperm combines with an egg that has a little a? A big A sperm and a little a. Well, we're going to get a zygote that is big A, little a. She or he is going to be heterozygous. All right, this one here is homozygous. And then, so you just move these 2 cells into that zygote. All right, let's do the same thing down here. We got a blue and a blue. And I know everybody loves making Punnett squares. And again, a lot of us did this in middle school, but it's okay if we didn't. I'm going to put a little a here because dad's chromosome has the little a and mom's chromosome has the big A. And then over here, again, a little a, and over here, a little a. But there's one thing you guys should notice. Let's see if Mrs. Doherty's prepared with her highlighter. There we go. That one's junk. These organisms, these fertilization events, they all are going to be what? What's their phenotype going to be? All of these are going to be normal, meaning these fertilization events, the children do not have sickle cell anemia. no sickle cell anemia because they have at least one dominant allele. Now this fertilization event over here, I'm just going to use a different color highlighter. I can't believe I had another color highlighter in my drawer here. This child is going to have sickle cell anemia because they have two little a's. They have the recessive. Okay, so it doesn't mean that this Punnett square does not mean that that this couple is going to have 4 kids and 3 of them are not going to have sickle cell anemia. What it is used to do is predict the probability. So look, if you have mom is heterozygous and dad is heterozygous, there's a 3 out of 4 chance that their child is not going to have sickle cell anemia. But there's a 25% chance, 1 out of 4, that their kid is going to have sickle cell anemia. So if you have 2 heterozygote parents and they decide to have a baby, there's a 25% chance that their child could have sickle cell anemia. So I know we can all write letters in boxes and move them into boxes like you did in middle school, but what I really want you to understand here, girls, is what the letters on the sides of the Punnett square mean. So if you remember from middle school, if you were asked to meet somebody that had big A, and big A, little a, these are the parents. Mom has the genotype big A, and so big A, little a, and so does dad. You can all make these boxes. Okay, and then you might have learned that there's a 3 out of 4 chance that the kid is going to not have sickle cell anemia, and there's a 25% chance that the kid is not going to have sickle cell anemia. But it doesn't mean that you understand what is on the sides of the Punnett square and what's inside the Punnett squares. Okay, what's on the sides are the possible alleles that are in each gamete. Dad could make a sperm that has a big A chromosome or a little a chromosome. Mom could make an egg that has a big A chromosome or a little a chromosome. And if this sperm combines with this egg, those 2 chromosomes come together in fertilization and you get the zygote with 2 chromosome 11s. So let's go to this question. What do the letters on the sides of the Punnett squares mean? They are the possible allele in the gamete. So you could have a sperm with a big A allele or a sperm with a little a allele. What do the letters inside the boxes of the Punnett square indicate? The possible or potential genotypes of the offspring. Okay, so the zygote is the offspring. A zygote's a fertilized egg. So hopefully by the end of this video, you'll have a much better understanding of what a Punnett square is. Like this was Punnett square for middle school. This is Punnett square from Mrs. Doherty's class, right? You can see that we drew the egg. Inside the egg is one of the 2 chromosome 11s. So what that means is on chromosome 11, there could be a big A allele. On the other chromosome 11, since the mom's heterozygote, we wrote it up here, she has a little a allele. Okay, and then what's inside the boxes are the possible zygotes produced by fertilization. So is it possible, get back up the truck. Is it possible for 2 normal parents to have a child with sickle cell anemia? Well, let's check it out. Mom here is normal, right? She does not have sickle cell anemia. Dad is normal. He does not have sickle cell anemia. But both of them are what we call carriers, which means when they don't have any type of sickle cell disease, but they carry the allele, so they're carriers. So if you've heard that a person is a carrier of a certain genetic disease, it means that the disease is recessive, right? Little a is the recessive condition, and that's abnormal hemoglobin sickle cell disease. So can two people that don't have sickle cell disease have a child with sickle cell disease? You bet they can, right? Well, let's kind of back up the truck. Dad is little a. Where's the red? Because loving him was red. Oh, Mrs. Doherty, what did you do with your red? Hopefully this will do. How did I lose the red? Right? These guys made each other. This could end up in an egg, and this one could end up in a sperm. So if mom's egg contains the little a allele and dad's sperm contains the little a allele, you're going to get a zygote that is little a, and they have sickle cell anemia or sickle cell disease, whatever you want to call it. Okay. All right, ladies. Oh, one more thing I wanted to show you. So I made this little Punnett square box a few years ago. I just want to show you this. So I'm going to use these little spindles here I got from Michael's. Okay, we're going to let the big spindle represent big A and the little spindle represent little a. And look, see how the colors coordinate? This will be mom. Mom has a big A allele and a little a allele. And dad has a big A allele and a little a allele. Okay, so a big and a big, those two combine, ka-chunga, ka-chunga, you get big A, big A. I'm just going to put those back in there for reference. You have a big A sperm and a little a egg, ka-chinga, ka-chinga. You get a big A, little a. I'm going to put that back in there just for fun. Okay, if a big A egg gets fertilized by a little a sperm, ka-chinga, ka-chinga. Or we can get a little a egg and a little a sperm, and they can combine and you'll get little a, little a. Okay, so here are the possible zygotes, and here is the gamete content, the alleles that are in either the sperm or the egg. So hopefully that helps some of our visual learners out there. And one more time, just for fun, mom is big A and little a. Dad is big A and little a. But only one of these possible two, chromosome 11s, goes in the egg. Only one of these possible two chromosome 11s go into the sperm. So if we get a little a and a little a, this is now the kid. This child is going to have sickle cell anemia. Okay, ladies, so hopefully you understand a little bit more about the Punnett square, comparing this, what you learned in middle school, to maybe this, what you've learned with me. And it's really important that you understand what is on the sides of the Punnett square and what's on the inside of the Punnett square. Okay, bye guys.